Welcome back to the clustering module. So far, we've learned what are clusters, what are the different properties of clusters, and we also looked at the different applications and use cases of clustering. The aim of clustering is not just to make clusters or random clusters, but to make good and meaningful ones. Remember these two cases we saw in the previous video. Case 2 makes more sense. And hence the clusters in case 2 are better and more meaningful as compared to the clusters that were made in case 1. Here we used only 2 features, so it was easy for us to visualize and decide which of these clusters is better. Unfortunately, that's not how things work in the real world. In the industry, we will have far more number of features. Let's take the customer segmentation example. Here, we can have features like their income, occupation, gender, age, and much more. So visualizing all these features together and deciding better and meaningful clusters would not be possible for us. And hence we can make use of the evaluation metrics for evaluating the kind of clusters that we've created. First evaluation metric that we can use to check our clusters is inertia. Let's harken back to our customer segmentation example. Recall the first property of clusters that we discussed. The points within the same clusters should be similar to each other. Remember that? This is what inertia evaluates. It tells us how far the points within a cluster are. So it calculates the sum of all the points within a cluster from the centroid of that cluster. We calculate this for all the clusters. And the final inertia value is the sum of all these distances. And we'll call this distance within the clusters as intra-cluster distance. So in short, inertia gives us the sum of intra-cluster distances. Now, what do you think should be the value of inertia for a good cluster? Should that value be small or large? If you look here, we want the points within the same cluster to be similar to each other. And hence the distance between them should be as low as possible. Keeping this in mind, we can say that lesser the inertia value, the better our clusters. Let's put a formula around calculating inertia. And here you go. We take the sum of distances of the points from the centroid of the respective clusters. Here, Wik is a variable which will be equal to 1 if the point xi belongs to cluster K. Otherwise, if the point does not belong to the cluster K, Wik will of course then be 0. Xi is the ith point and mu k is the centroid of the cluster to which the point xi belongs. We iterate it for all the points in clusters and then calculate the sum. We want to minimize this inertia value in order to have better and meaningful clusters. We can also use the Dunn index to measure how accurate our clusters are. Let's take a look at this Dunn index in a bit more detail. We've seen that inertia tries to minimize the intra-cluster distance. So eventually it is trying to make more compact clusters. Let me put it this way. If the distance between the centroid of a cluster and the points in that cluster is small, it means that the points are closer to each other. So inertia makes sure that the first property of clusters is satisfied. But it doesn't care about the second property, and that is a problem. That property stated that different clusters should be as different from each other as possible. This is where the Dunn index comes into play. Along with the distance between the centroid and points, it also takes into account the distance between two clusters, which we'll call the intercluster distance. Let's put a formula around Dunn index. And here you go. Dunn index is the ratio of the minimum of intercluster distances divided by the maximum of intracluster distances. And we want to maximize the Dunn index, right? Because more the value of the Dunn index, the better the clusters. Let's understand the intuition behind Dunn index. We want to maximize the Dunn index, and in order to maximize a value, the numerator should be maximum. Simple math, right? Here, we are not taking the maximum of the intercluster distance, but the minimum. So the distance between even the closest clusters should be more, which will eventually make sure that the clusters are far away from each other. Also, the denominator should be minimum to maximize the done index. Again, it's simple math. Here we are taking the maximum of intra-cluster distances. The intuition remains the same. The maximum distance between the cluster centroids and the points should be minimum, which will of course eventually make sure that the clusters are compact. To make sure that both the properties of clusters are satisfied, we try to maximize the done index, which ensures that the clusters are compact and far away from each other. These two are common evaluation metrics that are generally used to evaluate clusters. In the next video, we'll deep dive into different clustering techniques. I'll see you there. Thank you.